In this video follow along, we're going to get some practice doing cyclohexane chair configurations. Now, this is all about a perspective drawing, and we just have to get really used to using this perspective because the chair conformation more accurately represents what a cyclohexane looks like from a model perspective, right? This is not a flat system. The chair really helps us understand three-dimensionally what's going on here. And in order to do the chemistry that we're going to see in the subsequent chapters and to build accurate transition state models, we have to be very comfortable and familiar with drawing the cyclohexane chair. So we gotta not be afraid of it. So let's go through a review of cyclohexane chair configurations and drawing them and understanding the axial and equatorial relationships. So the way that I have the cyclohexane drawn on the left, I consider this to be more of a 2D model, right? It's kind of a flat-looking two-dimensional model. The chairs drawn on the right represent a 3D model. And to help us augment this 3D nature, I need you to understand that the bottom edge, I'm going to darken it. The bottom edge is the one that's coming out towards us. So if it helps you with your perspective, let's darken the edge of the bottom so that you can kind of see this perspective, like it's coming out at us. All right, so now what we want to do is get really good at drawing chairs. In a face-to-face scenario, I would have students go up to the board and draw. And the first thing that students will do is they draw really, really big chairs. It's like in the comfort zone. Let's draw it really big. What I'm going to try and have you guys do is not draw them as small as I have in these images, but really on a piece of paper, just practice drawing both the first and the second chair configurations. Understand that these are the same and they are in equilibrium. They are flipping back and forth, flip, 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 flip. And when I say the word flip, I don't mean flip it like a pancake. I mean, the word flip is kind of an annoying term that we use. It actually should be twist. It twists, 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 twists. Okay, so in twisting, it's changing its configuration. I can twist at the waist to stand up, or I can twist at the waist to sit down. I'm still me. I'm still the same molecule, but I'm twisting to put myself in a different conformation. You could say, conformation 1 is the chair in one position, and conformation 2 is the chair in a second type of conformation, just by twisting. Okay, so I'm just going to practice drawing the first one. Now, if you'll notice, I think it looks like, well, I usually tell my class that it kind of looks like a bird. You can draw a T-butyl bird with these T-butyl groups axial down. You can see it's like a little bird, right? With his beak. Here's his yellow beak. So the way that I get used to drawing these chairs is I think there's bird looking down, parallel line, tail up. There's its feathery tail. Duck beak down or bird beak down, parallel. And again, the front one is the one that's closest to you, so that one's going to extend further in the parallel line scenario. So you can practice drawing these duck beak down, parallel, tail. Okay? There is practice for one. Let's do practice now for the chair twist. Unfortunately, organic chemists call it the chair flip, but like it's not a pancake, it's just twisting. Now the duck is looking up. Something caught its eye. Parallel, parallel, tail down. Okay? Point that triangle towards the sky. Parallel, parallel, down. I am far better at drawing the conformation 1 over conformation 2. I don't know. You're probably going to find, like, being righty or lefty, there's going to be one that you're like, yeah, I draw those like a boss. And then the other one, you're like, I look like a baby drawing. Well, that's my conformation 2. I never naturally go to this one. I can draw it, but it's not my best. Maybe I need more practice. So practice drawing them both, you know, so that you can draw both of them on command. Okay, that's the first step. Now I need you to remember what wedges and hashes mean. We use wedges and hashes only on the 2D drawing. You do not use these when you're doing chair configurations. Okay, so you can see down below, I've drawn A and B. I'm drawing them in the flat looking 2D drawing with the cyclohexane all in the same plane as it looks. This is the above view. And so what you'll notice is that in this above view, in the 2D drawing, the OH in A is considered up. The OH in B is considered down. Okay? Now let's just take a quick look at both of these molecules and compare. Going back to your stereochemistry unit, ask yourself, are A and B the same or different? Are they the same or different? Which is it? Well, to answer the first question, are the two compounds below the same? The answer is no, they are not. If you try to overlay them, just take B and try to overlay it on top of A, they won't overlay because of the stereochemistry at the two chiral centers. There are two chiral centers. Each of these is a chiral center. And then there's no internal plane of symmetry, so they're not meso compounds. So indeed, these are different molecules because each one of their wedge hash is the opposite. So what are they? They're a type of isomer, specifically enantiomers. Enantiomers are mirror images. Now, I think the quick and easy way to distinguish enantiomers is when you draw the carbon framework. So the carbon framework is here. Okay, now when you draw the carbon framework the exact same way, you put the ethyl at the position to the right with the alcohol straight up, you can then do a direct comparison. Enantiomers are going to have all opposite wedges and hashes. So if everything in A that was a wedge became a hash in B and vice versa, then you're dealing with enantiomers. Diastereomers are when not all, any other mixture of change, but not all of them opposite. Not all opposite change. So an example of a diastereomer would be maybe keeping the alcohol but changing the ethyl. The relationship between these two are diastereomers. How about we'll call this C. C and A are diastereomers. Let's call this one D in the middle here. What is D's relationship to A? If you said the same, you would be correct. This is where you can actually pancake flip them to get the ethyl on the same side. And when you flip it, right, from a perspective, these are the same molecules. A and D are the same molecules. Therefore, D and B must be what? What's their relationship? Well, if A and B are enantiomers and A and D are the same, then D and B are also enantiomers. Okay, so that was a quick lesson in stereochemistry, reminding you of the relationships to be aware of. Now, can A be converted to B? Now remember, A and B are enantiomers. Can A and B be converted without breaking any bonds? Just by twisting. The answer is no. If I drew A as a chair in a chair conformation, twisting it to the second conformation, a 1 chair, in equilibrium with its chair, excuse the term, flip, does not change the stereochemistry. Okay, there is no bond being broken from 1 to 2 in the conformation. Just like I'm still me when I sit down. I don't have to break my legs off to sit on the couch, right? I'm just twisting and reconforming. So that's the key here. When we draw a cyclohexane molecule using chair representation, or 3D, it's just another perspective, and we can't lose the original stereochemistry beholden of the molecule. Up stays up, down stays down. Conversion between chair 1 and chair 2 is just flipping a conformation. Okay, so let's take a look at chair 1 in the figure here. I've highlighted a specific carbon so that you can track that same carbon from left to right. It's why I usually like to indicate the duck beak, because the duck beak, if this is carbon 1, then this is carbon 1. The duck beak looks down, that's the highlighted one. The duck beak looks up, that's the highlighted one in the second chair configuration. All right, so if you take a look, H1, I'll start highlighting these to follow along. H1 is most certainly axial. It is in the up position or the down position, right? So if you look at a chair, the axials are the easier ones to spot. Those are the ones that go up, down, up, down, up, down. Notice that because my bottom edge is in the front, when you draw that axial in the back here, it has to look like it's behind. So you kind of make it look three-dimensional in nature by running it to look like it's behind. Do not do this. That is like an MC Escher art nightmare where it looks like some crazy, weird, staircase going in and out. Like, it doesn't make any sense to my eyeball, right? Because the bottom edge is in the front, so you can't have a back down axial going in front of your front edge. It doesn't make any sense. So you have to make the back axial, look like it's in the back. So you kind of don't draw it all the way through, so that your eyeball perspective works, okay? So the axials are the easier ones to draw. The equatorials, if you draw the axials first, it'll be much easier to see where the equatorials are. Never draw your equatorials inside the ring. Notice that none of my red lines went inside the ring. Okay, always push them out. What you'll notice is that the equatorials almost mirror the parallel beak lines. They go almost with the beak. Okay, and the ones on the end just go out. Okay, so that's what you're going to follow. Axials in black, the equatorials in red. Now look at H1. H1 is axial, it's going straight up, and so it's got the up designation. And the up and down is always relative to the other group on the same carbon. So H1 is on the carbon in the back, and it's shared with H2, right? H2 is also on the same carbon. Which one is up and which one is down? Well, I think it's easiest to just assign the axial one. Axials are easy to assign. Look at H4. H4 is definitely pointing down. H1 is definitely pointing up. So we can fill in the blank here. H4 is definitely down. H1 is definitely up. H4 is definitely axial. H1 is definitely axial. H2 and H3, therefore, are equatorial. You can't have two axials and two equatorials on the same carbon. And if it's tough to identify the equatorial as either up or down, take a look at its axial partner. H1 is axial up, therefore H2 must be equatorial down. H4 is axial down, therefore H3 must be equatorial up. So assign the axials first, and by default, you'll know what the equatorial is. Okay, in the ring flip, notice that I'm going to highlight H1 right here and H4. The beak flipped up. You can almost see it like flipped up. And now, in flipping up, the H3 is axial. So H3 is now axial. H2 is now axial. H3 is definitively axial up. H2 is definitely axial, but it's pointed down. Therefore, H1 must be equatorial and up. Because if H2 on the same carbon is axial and down, then H1 must be equatorial and up. If H3 on the same carbon with H4, if H3 is axial up, then H4 must be equatorial and down. Now, what I want you to notice is that H1 through H4 went up, down, up, down. H1 through H4 went up, down, up, down. The up and down do not change. That is what defines stereochemistry. And we know that the stereochemistry doesn't change. It is what it is. Even when you're flipping and twisting the ring, you're not changing the stereochemistry. The molecule is set, okay? What does not define your stereochemistry is axial and equatorial. Those are just conformational changes. I'm sitting up, I'm standing, I'm sitting down, I'm standing up, I'm lying down, I'm standing up, but I'm still me. I'm defined. I am who I am. Okay, that's not going to change, but I can change my position. And so there are going to be conformations, axial and equatorial, depending upon what groups are substituted on the ring, that will make a big difference in the energy. And that's what we're going to study in chapter 2. So you've got to be really good at drawing these axial, equatorial groups and going between the 2D, 3D, backwards and forwards interconversions for representation. So let's get some practice here. Okay, draw both chair conformations. All right, first I start with the one I like. I'm going to enhance the bottom edge for ease. Okay, now what I like to do is say, I'm going to do the same thing here since I have 1, 2, 3, 4, 5, 6. It doesn't matter where you decide to number. I'm just giving you this as an example. There's no right or wrong. This is not IUPAC naming. This is just me trying to convert a perspective drawing from 2D to 3D. So what I like to do is, if I've drawn my cyclohexane chair, we'll call it chair 1, since I made the bottom edge coming out at me, I'm going to enhance the bottom edge here as well. I've chosen to start over here. Okay, so I'm going to make this 1, 2, 3, 4, 5, and 6. Okay, you could have, it doesn't really matter. Like I said, as long as you keep the bottom edge, you could have decided, all right, I'm going to do this bottom edge here and here and here and make this 1, 2, 3, 4, 5, and 6. Make it easy on yourself and try to do this type of analysis. Don't start numbering up at your alcohol. Like, try to keep it as close to your drawing as possible. All right, so sticking with this, if you look at carbon 1 has a methyl group. So I'm going to want to draw 2 bonds at carbon 1. Axial down and equatorial up. The beak kind of guides you. What you don't want to do is this. You don't want to draw axial up here and equatorial. This makes no sense. You've got to remember that these carbons, right? Each carbon is sp3 hybridized, which means that they're tetrahedral, which means that the bond angles are about 109 degrees. Do you think that you have made 109 degrees? I mean, look at this. You've got this massive space down here, like 180 degrees. This is not a tetrahedral looking system. So, get out of that. You can't put your axials up in the acute angle. It has to be, draw your axial first. This is the duck beak's pointing down, so draw your axial down. That means the equatorial, space it out, looks like that. Then you go to the methyl. Your methyl, because it's on a hash, means that it's down. That's easy. I put the methyl here. Carbon 2 doesn't have any substituent on it, so I'm going to skip carbon 2. Carbon 3 has a substituent on it, so let me draw both axial and equatorial, and since the triangle is sort of pointing downward, I'm going to draw it like this. I go back and I look, that isopropyl group is indicated as down. So I'm going to draw the isopropyl group here, and the hydrogen goes here. There's nothing on carbon 4. Carbon 5 has an alcohol, so I'm going to draw both lines. Notice I drew it, that axial down in the back. I look to the alcohol and I see that it is up, it's wedged. Well, the axial is down, so the equatorial must be up. So I'm going to draw the alcohol equatorial and place the hydrogen at the other position. I've now completed the first chair configuration. Let's draw the chair flip or twist. God, I hate drawing these sides. I'm sure you guys are with me. They just don't look as spectacular as my other ones. That'll work. Let's color our edge. The bottom edge is coming out at us. All right, so this was carbon 1, the nose, right? The nose was carbon 1. So the nose is carbon 1. 2, follow your edge. 3 is in the front. 4, 5, 6. Okay, I've mapped it. Now let's go through it. I'm going to have to draw something at 1, but now my duck beak is like this. The methyl is down. Down stays down. The methyl is equatorial now and down. The hydrogen is now up and axial. Skip 2, go to 3. 3, draw your bonds first. There's my axial and equatorial. 3 has a down isopropyl. Skip 4, go to 5. Draw your bonds first, fill them in after. Your alcohol is up, wedge, so that means it's up here. And that is the chair flip. I've now successfully drawn both conformations for the cyclohexane given these 3 substituents. Now, one of them is going to be lower in energy than another, and that's what we're going to spend some chapter 2 quantitatively identifying, the quantitative energy difference between these 2 configurations. So in order to do that, you got to be good at drawing both conformations. Let's do the next one. I'll be quieter on the commentary on this one. You can follow along. All right, I'm going to start, well, I've got this down here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Oh, 5 and 6. I'm just working 4, 5, and 6. So 4, 5, and 6. Okay, now let's place them. At 4 on the right, we have a methyl down. The bromine at 5 is up. The alcohol at 6 is up. That is one conformation. In equilibrium with its twist form, the flip. Highlight my edge. The beak is now pointed up. That has to be the same carbon. 4, 5, 6. So at 4, at 5, and at 6. 4 is down methyl. I always go back to my original, and you can double check your work afterwards. I always look back at my original 2D. 5 is up bromine, and 6 is up alcohol. And that way you can check alcohol axial, alcohol equatorial, bromine equatorial, bromine axial, methyl equatorial, methyl axial. I seem to have kept the ups and downs, but I did exchange from axial to equatorial in the conformation change. So that was a good thing. Success. Lastly, we should be able to convert from the chair back to the 2D drawing, because the 2D drawing, ultimately, when you publish a paper, more often than not, people are publishing it in the 2D structure with wedges and hashes because they're easier to look at. And they only show these chairs when they're analyzing transition states or modeling. So let's practice converting from the chair back to the 2D. I'm going to highlight my front edge again because it's coming out at me. I'm going to number 1, 2, 3, 4, 5, 6. I'm going to highlight the bottom edge of my cyclohexane. And since I started highlighting at 1, I'm going to try to map it like so. Now carbon 2, feel free to draw in the missing bond. That one's a hydrogen. So relative to the hydrogen, that ethyl is axial and it's up relative to the hydrogen. So at 2, I have to draw a wedge ethyl. Skip 3, there's something at 4. Draw in the missing bond. That's the axial hydrogen. So if the hydrogen is axial up, the bromine must be equatorial down. So 4 has a hashed bromine. And so you can clean it up and draw it nicer without your little cheat shadings and come up with this as your product. Or I should say as your compound perspective drawing. This is your 2D, and this is your 3D. So on exams, when I ask you for your answer as a 2D or as a 3D, you'll know what I mean. Let's do the last one. I'm gonna shade that bottom edge. It's coming out at me. Numbering 1, 2, 3, 4, 5, 6. I can shade the bottom edge. 1, 2, 3, 4, 5, and 6. At carbon 1, there is a methyl and an alcohol. The methyl is down and the alcohol is up. Methyl is down, alcohol is up. Skip 2, skip 3, 4 has a chlorine on it and a hydrogen. The hydrogen is down, so the chlorine on 4 is up. Skip 5, 6 has a hydrogen up, but the ethyl is down. So 6 has a down ethyl. And we can rewrite and clean this up nicely as a down ethyl, a down methyl, an up OH at 1, skip 2, skip 3, 4 has the up chlorine. And there you have it. Practice, practice, practice. You guys will be getting very good at this and doing it in your sleep, and it won't be any problem at all, so that when we start analyzing the energies of these systems, you won't be tripping over yourself trying to remember how to do and represent these cyclohexane systems.